The laws of physics are not constant, and it changes everything. The constants aren't constant. There's a slow leak in reality, and it's been seeping through our rulers and clocks for a century. Not a theory, anomalies in quasar light, ancient uranium mines that ran themselves, and clocks that disagree by a whisper when you move them upstairs. Institutions call it calibration. Some call it heresy. We're going to follow the evidence anyway. 3 questions will anchor us. What might be changing? How would we actually know? And what breaks if it is? This isn't abstract. If the settings drift, so do time, size, and cause. Your watch becomes a weather report. The day the meter lied when C started slipping. The stakes land fast. If the speed of light even nudges, every distance we infer from light's travel time slides. Every clock that leans on electromagnetic transitions tilts, and the order of cause and effect starts to wobble at the edges. Airlines don't fall out of the sky if C moves in the 15th decimal, but the scaffolding of measurement, the quiet agreements that let satellites talk and telescopes triangulate, would flex. To understand why anyone thought C might be slippery, we need to go back to the messiness before precision smoothed the story. Early 20th century labs measured light speed with rotating mirrors, toothed wheels, cavities that rang like tiny bells. Results marched toward a consensus, but they marched with scuffed boots, dust on lenses, air's refractive index sneaking in with the weather, mirrors that warmed under lamps and expanded enough to matter. The numbers tightened, yet never stopped whispering about their conditions. Mid-century, microwave techniques sharpened things. Resonators gave fewer excuses, until a new problem appeared: timing jitter. The electronics that started and stopped clocks had personality. A technician could breathe near a cable and unknowingly shift a nanosecond. Meanwhile, air wasn't innocent. A lab at sea level with humid air wasn't the same optical world as a dry mountaintop. Even the glass in a window aged, and coatings changed subtly with temperature. By the 1970s, metrologists were tired of chasing the gremlins. They weren't giving up on truth, they were chasing stability. The solution was bold. Instead of measuring C, define it. In 1975, C was recommended at 299,792,458 ms. In 1983, the meter itself was redefined so that C is exactly 299,792,458 meters per second. Elegant, brutal, final. From that moment, anyone measuring C was, in practice, measuring the length standard derived from atomic transitions and counting how many light seconds fit into their apparatus. That solved a problem and created a new one. Constancy by decree isn't constancy by nature. If you freeze C in the definition, you remove a direct diagnostic of drift. You trade an unruly ruler for a pristine one, then discover you can't tell if the wall quietly moved. Metrology thrives on this kind of bargain, but it means you need different suspects to interrogate if you want to know whether the universe's knobs turn. Before we leave that change, remember a micro story from a lab no one writes songs about. A graduate student is aligning a cavity. The room's air conditioner kicks off. The temperature drifts by half a degree. The cavity length expands by a few atoms worth, the resonance shifts, and the speed of light inferred from this setup migrates, not because the cosmos flexed, but because the box breathed. Those are the ghosts that haunted variable C rumors. And they're exactly why a definition felt like relief. Still, the relief masked a profound question. If C is baked into the meter, what's left that we truly measure that ties together electromagnetism, quantum mechanics, and relativity? Enter a dimensionless constant, one that can't be redefined away by changing units. The fine structure constant, alpha, 1137 and change, sets the scale of atomic structure. It lives in the spacing of spectral lines and the strength of electromagnetic interactions. You can't hide it in a definition, because it's a pure ratio. Here, S where the stakes rise again. If alpha drifts, chemistry retunes. Electrons nestle closer or farther from nuclei. Spectral fingerprints shift. Stars fuse differently. A minuscule change over billions of years would leave quiet graffiti in the sky and in the rocks. And unlike C, alpha can be hunted in many places. In astrophysical spectra, in the ruins of a 2-billion-year-old natural nuclear reactor, and in the beat notes between today's best clocks. But let's not jump too fast. There's one more twist in the meter-lied story that teaches caution. After 1983, when someone reported a variation in C, critics could rightly answer, "You're reporting how your apparatus measures length and time within the new definitions. Any drift lives in your materials, your lasers, your electronics, or in nature's constants that those devices depend on." That's the subtle pivot. We stopped asking, "Is C changing?" and started asking, "Are the deeper, dimensionless couplings changing?" Meanwhile, something else was happening in the background. As lasers stabilized and frequency standards improved, labs discovered that every component had a personality. A fiber's refractive index twitched with strain. Coatings on mirrors aged under light. Vacuum chambers that seemed quiet had outgassing rhythms. Metrologists became part physicist, part therapist, coaxing instruments into silence long enough to hear the universe. And in those silences, they heard nothing obvious. But nothing isn't the end of the story. Nothing sets the limits that define the hunt. Okay, stakes, action, and the impact of a definition. The day the meter lied wasn't a scandal, it was a turning point. We fixed a number to anchor measurement. We lost a direct test. Therefore, we needed a new witness that nature couldn't duck with a unit change. Alpha raised its hand. In the next act, that whispering constant steps into the light and distant quasars, light that left when the universe was young, become our cross-examination. The fine structure whispers, alpha's uneasy consistency. Alpha isn't a speed or a mass. It's a ratio that tells electrons how tightly to hug a nucleus and how photons talk to charges. Change alpha a hair and hydrogen's spectral lines scoot. Change it more and stars rehearse a different script. That's why this constant is the witness we needed. You can't redefine a pure number away. If it moves, the universe leaves receipts. And here's the thing, you'd see it everywhere at once. In quasar barcodes, in a 2-billion-year-old reactor's ash, and in the way today's best clocks quietly disagree. So where do you look? First, the sky. Distant quasars light up clouds of gas between us and them, carving barcode patterns of absorption lines. Those lines aren't just pretty, they're rulers etched into the past. In the late 1990s and early 2000s, a group started stacking those rulers using the many multiplet method. Instead of relying on a single doublet from, say, magnesium, they mixed transitions from different ions. Iron, chromium, nickel, each with a different sensitivity to alpha. If alpha changed, the spacing between these lines would shift in a telltale way, across species, not just within one. The initial hint was strange. Keck Observatory's spectra suggested alpha might have been smaller when the universe was younger. Then new data from the Very Large Telescope, looking in a different part of the sky, nudged the other way, alpha slightly larger. Put together, the anomaly didn't average to zero. It arranged itself like a dipole. One half of the sky preferred a nudge up, the other a nudge down, at roughly parts per million. Not a loud shout, but a whisper with direction, consistent with the Webb-Murphy analyses that sparked 2 decades of follow-up. Here's where the human part kicks in. In one office, a postdoc scratches out sensitivity coefficients and says, "That pattern is hard to fake." In another, a spectroscopist groans, "It's the wavelength calibration." Old-school lamps that mark the pixel-to-angstrom mapping can have tiny distortions across orders. Slit illumination shifts. Temperature gradients inside the spectrograph bend glass by a micron. A 3 a.m. calibration check turns into a ritual. Power cycle the lamp, take a second exposure, overlay lines, look for the serpentine wiggle that ruins everything. Meanwhile, others point to Mg isotopes. If the relative abundance in a cloud is Earth-like, the line centers drift a bit. That can masquerade as alpha moving. The debate grows teeth. Either the universe has a preferred direction at the parts per million, 10^6 level, or a dozen small, harmless, assumptions conspired to draw a dipole on our sky. Parallel to the telescope arguments, an older witness sat in rock, Oklo. 2 billion years ago in Gabon, a uranium deposit went critical. The isotopes it left behind depend sensitively on nuclear resonance energies, which in turn depend, through a messy chain, on alpha and on the strong force. When physicists back out what those resonance shifts would be if alpha had drifted, they find room for only tiny changes, parts in 10^7 or tighter over billions of years, in line with classic Fujii-style analyses. Not zero, but thin margins. Oklo fenced off the wildest possibilities and forced the sky claims to thread a narrow alley. Back on Earth, the lab clocks woke up. If alpha breathes, different atomic transitions should disagree in time. A strontium optical lattice clock ticks with electrons dancing between energy levels that scale one way with alpha. An aluminum ion quantum logic clock scales another. A microwave hydrogen maser tunes yet another knob. Compare them year after year, through seasons, solar cycles, and altitude changes, and you're not just keeping time, you're eavesdropping on the universe's control panel. Here's a micro story from that front line. In a dim room, atoms cool to microkelvin, suspended in a web of laser light. A technician nudges a piezo by a billionth of a meter to kill a drift. The beat note between two clocks, the rhythmic whoop-whoop in a spectrum analyzer, shrinks to a thread. Weeks later, they fold the data, any sinusoid with a 1-year period, any drift linear with time, mostly silence. The limits tighten. If alpha is moving today, it's doing it below the 17 per year mark. Brutal. Not a death sentence for variation, but a cage with bars close together. While that was happening in the lab, the telescope world upgraded its ears. Laser frequency combs replaced calibration lamps. Vacuum-stable spectrographs sat on granite slabs, temperature controlled to the millikelvin. New surveys reported nulls or small shifts without a clear dipole. The fight became honest. Remove every known systematic and see what's left. Some datasets still prefer a dipole by a few sigma, others don't. Either way, the error bars got honest enough to matter. What nobody knew at the time, as the first dipole plots made the rounds, was just how much these arguments would feed cosmology and ignite careful reanalyses of isotropy itself. If alpha varies across the sky, isotropy, the core assumption that physics looks the same in every direction, takes a dent. If alpha drifts with cosmic time, the physics of recombination shifts, which slides the cosmic microwave background's acoustic peaks. That ripples into how we infer the Hubble constant and the age of the universe. It's not just chemistry, it's the scaffolding of cosmology. This was the moment everything changed in tone. The question stopped being, is alpha constant? And became, if it isn't, what's moving underneath? Because alpha isn't a single knob. It's a ratio involving the electron charge, Planck's constant, and see something deeper would have to be flexing. And if something deeper flexes, it can imprint a direction, a time dependence, or both. In the aftermath of 2 decades of sky and clockwork, we sit with an uneasy consistency. Alpha looks stubbornly steady in the lab today. The ancient rock allows only tiny drifts over eons. The sky still holds a hint that could be calibration or could be a cosmic breeze. Life's recipe seems robust here, maybe only here. To understand why alpha would move at all, we need a suspect that can turn knobs gently, everywhere, and yet hide from most tests. That suspect isn't a new particle we catch in a collider. It's a field that bathes space, slow rolling, changing the rules by whispers. If it's there, constants aren't constants. They're the local weather of a deeper climate. Ghosts in starlight, quasar spectra, and the dipole claim. While the lab tried to hear alpha breathe, the sky whispered in a different accent. Quasars, bright beacons at the edge of time, shine through filaments of intergalactic gas. Each cloud along the line of sight stamps a barcode of absorption lines onto that light. If alpha changed, the spacing of those bars would shift in a pattern you can't fake with a single element. It has to move across different species in a coordinated way. The many multiplet method was the scalpel. Instead of trusting one doublet, researchers lined up transitions from magnesium, silicon, iron, chromium, nickel. Each transition carries a sensitivity coefficient, call it Q, that tells you how much that line's energy shifts if alpha nudges. Stack enough lines with different Qs, fit them together, and any consistent alpha change pops out of the noise like a watermark. Here's the stakes. If that change points in one direction over there and the opposite direction over here, then the universe has a preferred axis. Cosmology assumes isotropy, that on large scales, it looks the same in every direction. A dipole in alpha dents that assumption. It doesn't smash it, but it forces us to redraw the frame we measure inside. Action step by step. Keck's high-resolution HL spectrometer gathered hundreds of quasar spectra. The fits leaned towards smaller alpha in the distant past along its patch of sky. Then the very large telescope in Chile, with a different spectrograph and a different view, suggested the opposite in its hemisphere, alpha a hair larger. Combine them and the map didn't flatten. It twisted into a dipole. One pole prefers alpha down, the other alpha up, at roughly parts per million. Meanwhile, something else was happening behind the terminal screens. Calibration lamps, thorium-argon sources, etched reference lines used to map pixel to wavelength. But those lamps weren't perfect. Lines blended, orders curved. Temperature gradients across a meter-long spectrograph nudged optics by microns, warping the dispersion relation. One night at 3 a.m., a researcher relit the lamp, took a second exposure, and watched the line fit residual snake by a few meters per second. Tiny, yet enough to mimic a whisper in alpha if you were unlucky and trusting. Critics traced distortions, small, smooth wavelength stretches that varied across orders. Slit illumination changed when seeing conditions wobbled. Fiber feeds reduced but didn't erase it. Some groups re-reduced the same raw data with different pipelines and watched the dipole amplitude inflate or deflate. Others targeted specific systems with narrow metal lines less prone to blends, and the signal weakened. Parallel action in a different lab. Laser frequency combs arrived. These devices paint an evenly spaced ruler of absolute frequencies onto the detector, replacing messy lamps. Spectrographs like HARPS and espresso were stabilized in vacuum, pressure locked, temperature held to the millikelvin. On these instruments, the calibration serpent had fewer places to hide. Early results leaned null or inconsistent with a strong dipole. Not a clean acquittal, just stricter cross-examination that put the boldest claims under pressure. Stakes for people showed up in small human ways. A grad student built a Monte Carlo to simulate quasar absorbers with non-terrestrial magnesium isotope ratios. Vary the isotopes, the line centers shift independently of alpha, smuggling in a false signal. Another team checked intra-order distortions by comparing telluric absorption lines imprinted by Earth's atmosphere with the lamp solution. The corrections helped, but didn't erase every anomaly. Across town, a different group reanalyzed only the highest signal-to-noise systems and found less evidence for any drift at all. So what did it change? Impact arrives in two layers. First, even contested hints forced the community to design instruments as if the dipole were real. Comb-calibrated, fiber-fed, vacuum-stable spectrographs became standard for precision cosmology. That engineering push pays dividends far beyond alpha. Exoplanet hunts, redshift drift tests, even measurements of cosmic acceleration with gravitational wave sirens cross-calibrated to optical spectra. Second, the combined datasets, Keck plus VLT, still prefer a dipole at a few sigma when analyzed in the original framework, even after known systematics are modeled. That preference isn't decisive, it's a standing invitation to try to break it. On the other hand, independent campaigns report nulls within tighter error bars. Either outcome tightens the noose. If variation exists, it must thread a needle between instruments, sky positions, and absorber chemistry. If it doesn't, we've just mapped the instrument ghosts with unprecedented fidelity, and that map now guides every new spectrograph design. Meanwhile, something else bubbled in theory. A spatial dipole is exactly the sort of imprint a light scalar field could leave if its value today varies slowly over horizon scales. If that field couples to electromagnetism, alpha becomes space's local weather. You'd expect mild gradients, not wild swings. You'd expect small temporal drifts, perhaps modulated by gravitational potentials, and you'd expect equivalence principle tests to feel a faint tug. That linked the quasar plots to laboratory searches and to lunar laser ranging in a single storyline. Human moment one more time. A researcher stares at residuals after subtracting every known distortion and whispers, "What's left?" Not triumph, not despair, just the feeling that either the sky is telling us a quiet secret or our instruments are almost but not quite silent. In the aftermath, the field moved with better tools, stricter priors, and a shared caution. Don't average away a signal, don't amplify a ghost. Even null results matter. They fence alpha's spatial wanderings to parts per million over gigaparsec scales, and its temporal drift to less than a part in 1017 per year today. While that was happening in Chile and Hawaii, a clue had been waiting in Gabon for 2 billion years, engraved in uranium and samarium. If the sky hints at a dipole, the Earth's crust holds a stopwatch, and that ancient clock has something blunt to say about how far alpha can roam. Reactor in the jungle, Oklo's ancient stopwatch. While telescopes argued with calibration lamps, a different kind of instrument was discovered in red laterite and jungle heat. In 1972, at the Oklo uranium mine in Gabon, a shipment's assay came back wrong. The uranium-235 fraction, normally 0.72% in nature, was short, not stolen, burned. The ore had less U-235 than any known terrestrial deposit should. Miners saw a bookkeeping problem. Physicists saw a fossil reactor. Here's why that mattered. 2 billion years ago, the natural U-235 abundance was higher. Radioactive decay hadn't yet whittled it down. Groundwater percolated through rich ore, moderated neutrons, and in pockets sustained a chain reaction. It wasn't mythology. It ran intermittently for hundreds of thousands of years as water boiled off. The reaction paused, water returned, and it resumed. Nature built a reactor with no blueprints, only geology and time. The stakes are sharp. A sustained chain reaction leaves fingerprints, isotopes out of balance, rare samarium and neodymium fractions that don't match ordinary geochemical processes. Those fractions depend on nuclear resonance energies, the precise positions where a nucleus is eager to capture a neutron. Shift those resonances a hair, and the reaction's byproducts change. Those resonance energies, in turn, trace back to the strengths of forces, primarily the strong force, but with threads to electromagnetism through the fine structure constant alpha. If constants drifted over eons, Oklo would show it in the ash. Action moved from shovels to mass spectrometers. Analysts pulled cores from the reactor zones, slicing time through minerals. They measured samarium-149, a notorious neutron poison, and its daughter samarium-150. They checked neodymium isotopes, xenon trapped in mineral bubbles, little time capsules of fission. The patterns weren't random. They matched what a reactor would cook, given cross-sections that depend sensitively on where a nuclear level sits relative to neutron energies in water-moderated conditions. Then came the hard part, mapping those fossil ratios back to physics knobs. The capture cross-section of samarium-149 spikes at a specific resonance about 0.097 eV if, 2 billion years ago, that resonance had shifted by even a few tens of millielectronvolts. The burn pattern would look different. Theorists built models that relate such shifts to underlying constants. Its messy, nuclear structure ties the strong interaction to electromagnetic effects, but within uncertainties, you can ask, how much could alpha have changed without wrecking the observed ratios? Impact, bluntly stated, not much. Analyses constrain the fractional change in alpha over 2 billion years to be at most parts in 10.7, with some studies quoting even tighter bounds, model-dependent. That's tiny. It doesn't call the sky's hints a lie, it fences them in. A dipole at parts per million over gigaparsecs might still thread that fence if local time drift is even smaller, or if other constants co-vary to keep nuclear resonances in place. But wild order-of-magnitude swings, Oklo says no. The tension wasn't just numbers, it was disciplines talking past each other. Geochemists warned that fluids moved elements after the fact. Could later groundwater shuffle samarium and neodymium, faking a reactor signature? Nuclear physicists countered with concordant evidence. Multiple isotopic systems pointed to the same burn story. Meanwhile, modelers argued about how to translate a resonance shift into delta alpha. The strong force's fingerprints are everywhere. If it budged too, you could cancel or amplify alpha's effect. The uncertainty fights were real. Human angle quick and clear. A French analyst leans over a sample in a quiet lab. The mass specs hum like a held breath. The readout steps through isotopes. The curve lands where a reactor's ash should. He doesn't cheer. He circles a point on the plot and writes, consistent with criticality. Across the Atlantic, a theorist scribbles on a whiteboard, arrows from E-rays to alpha MQ lambda QCD, then stops and underlines degeneracy. The data is beautiful, the inference is delicate. But even with modeling ambiguity, the takeaway held. Oklo is a time capsule for constants. It says, with Rock's authority, that if alpha slid, it slid within razor-thin margins over geological time. That doesn't kill variation, it calibrates it. It tells us the drift, if present, is slow or coordinated. It hints that nature could allow a field to move knobs while keeping certain combinations pinned, resonances preserved as other parameters flex. The fence is tight, yet not a cage for clever theories. Meanwhile, something else was happening in standards labs. As Oklo's constraints tightened, metrologists realized Rock had joined their team. Geology wasn't just scenery, it was metrology in deep time. If you want to claim a cosmic dipole, your model has to respect a reactor that ticked away in Africa and left us a ledger with samarium ink. The story started to braid. Sky spectra, ancient cores, and today's clocks, each with a different lever arm on the same question. One more reveal. Oklo's limits also slice into gravity's story indirectly, because any scalar that moves alpha tends to tug on masses unless exquisitely tuned or screened. If a scalar field modulates constants, it can couple to mass, and then equivalence principle tests, torsion balances on Earth, lunar laser ranging across the moon's orbit, feel its pull. The field can't be loud in one arena and silent in another without a mechanism. Oklo's quiet voice forces that mechanism to be clever, screened, or faint. So we leave the jungle with a stopwatch in hand. The ticks are billions of years apart, but they're clear enough to set boundaries. Thin margins still matter when you stretch them across the cosmos. And if drift hides within those margins, our most sensitive timepieces should be able to hear it, especially when we climb a staircase or wait a year. Time to listen with clocks that can hear the universe breathe. The clocks that can hear the universe breathe. If constants drift, time itself should carry the rumor. Not in fireworks, just in disagreements so small they hide in the 12th, 15th, 17th decimal place. That's where today's clocks live. They don't just tell time, they sample the laws of physics on different channels and let us hear if one of those channels drifts out of tune. Start with the cast. Strontium optical lattice clocks trap tens of thousands of atoms in a standing wave of light, freezing their motion to microkelvin so Doppler blur collapses. A narrow transition, an electron hopping between two nearly forbidden states, ticks at hundreds of trillions of cycles per second. Ytterbium does a similar trick on a slightly different frequency, with a different dependence on alpha. An aluminum ion clock, read out by dragging it with a logic ion, trades atom count for exquisite isolation. Hydrogen masers hum in the microwave, sensitive to different combinations of constants. Each species is a separate microphone on the same stage. The stakes are simple and sharp. If alpha or the electron-to-proton mass ratio nudges with time, these clocks won't agree forever. If a scalar field swells and ebbs with the seasons as Earth's orbit modulates the gravitational potential, a yearly sinusoid might slip into their beat frequencies. If the field has a gradient with height, two clocks at different floors could disagree in a way that isn't fully explained by Einstein's redshift. You don't need a thunderclap. You need the nerve to trust a whisper. Action unfolds in quiet rooms that feel more like monasteries than factories. Laser tables float on air. The light that interrogates the atoms is locked to cavities that barely expand when the building breathes. Temperature control isn't a thermostat on the wall, it's a fortress. People move slowly. A cable tugged wrong adds phase noise. A cooling fan replaced in a hurry makes a line width fattened by a few hertz and ruins a day. Here's a micro story that carries the texture. Midnight at a national metrology lab. On a spectrum analyzer, two razor-thin peaks, one from strontium, one from aluminum, beat to make a low-frequency tone. It's a soft, steady whistle, almost musical. A technician adjusts a piezo by a billionth of a meter to center a cavity. The whistle tightens. They step back. For the next 12 hours, the instrument just listens to the universe, counting difference ticks, folding them against a calendar. Daily, monthly, yearly. Meanwhile, across an ocean, a sister clock does the same. Fiber optic links braid the continents with frequency light. That's not internet. It's time shipped as phase-stable waves. A network of labs compares their ticks with fractional uncertainties near 1018. At that level, lift a clock by a centimeter and general relativity pulls a measurable shift. So they test that too, turning buildings into gravity experiments. You can hear the redshift with your instruments if you climb a step stool. Now the impact. After years of runs, season to season, solar maximum to minimum, the obvious hasn't appeared. No linear drift that stands proud of the error bars. No clean annual modulation across multiple species. The reported limits are brutal. If alpha is changing now, it's slower than roughly 1017 per year. If a coupling to gravitational potential exists, its coefficient sits under tight caps from seasonal and altitude-dependent comparisons. It's not nothing. It's a cage drawn with such fine wires that theory has to thread through with care. But silence isn't empty. It shapes the hunt. It tells scalar field models how gently to roll. It tells equivalence principle tests where to push. It tells quasar claims what amplitude won't survive the present day. And every null sharpens the tools. Laser frequency combs that connect optical ticks to the microwave definition of the second now span networks. Portable optical clocks ride in vans to compare mountain labs with sea-level basements, testing for gradients that a building can't provide. While that was happening in labs, engineers realized these clocks do double work. They're gravity sensors that read geodesy directly. Move one to a cliff top, and it reports the local gravitational potential through time dilation. National surveys use them to track groundwater and magma. It's practical, but it's also an audition for physics. If a field that modulates constants is screened or enhanced by mass, then comparisons over terrain might see a pattern that two side-by-side clocks miss. Human moments keep it real. A young researcher reprocesses a year of data after discovering a stray acoustic coupling in a cavity mount. The results don't change. Relief, then a post-it on the lab door. Silence is a measurement. Another team loses time to a fiber splice that looks perfect under a microscope but adds flicker you only hear at 1018. Weeks later, the beat note settles into a thread again. The line in the logbook reads, "Back to listening." And there's a reveal in the meta-story. Even nulls are pushing toward a leap, redefining the second in the optical, away from cesium's microwave transition, because the optical world gives more ticks per second and tighter control. That redefinition will lock our units to atoms that also serve as drift sensors. If the universe breathes, we'll be measuring with the very instruments that can hear it. The irony isn't lost on anyone. The act of pinning time cleaner makes it easier to catch time's rules flexing. Still, one suspicion lingers at the edge of these rooms. If the clocks stay quiet, maybe gravity will talk louder, because orbits integrate tiny tugs for decades in ways a week-long clock run can't. A field that grudgingly touches electromagnetism could pull more boldly on mass. Mirrors on the moon answer lasers from Earth night after night, and planetary orbits integrate tiny tugs over decades. If constants are coordinates in a deeper field, its signature might hide not in tick rates, but in how the solar system breathes. G, the slippery giant, why gravity won't sit still. If a field is nudging the constants, gravity is the obvious place to look. Not because it's easy, because it's unforgiving. Tiny changes in the gravitational constant G would accumulate in orbits, tides, star structure, even in how the early universe cooked light elements. A part per trillion wobble won't crash the solar system by Tuesday, but given decades of data, the system would flinch. And here's the uneasy part. Our laboratory measurements of G have been flinching for decades. The stakes are clean. G sets the scale of gravitational strength in Newton's law and seeds general relativity's geometry. If G drifts in time, the Earth, moon distance integrates that drift into a slow dance. If G differs in space, torsion balances and atom interferometers feel a faint sideways pull. If G is just hard to measure, then the apparent disagreements are systematic ghosts. We're left with a split verdict. Cosmology and celestial mechanics scream steady, while benchtop experiments can't quite agree on a number. Action starts with a simple-looking machine, a Cavendish torsion balance. Suspend a thin fiber, hang small masses on a bar, bring large masses near. The gravitational attraction twists the fiber by a hair, and that angle with careful calibration gives G it sounds Victorian and elegant. In reality, everything conspires against you. The fiber creeps, air currents cough, nearby trucks whisper vibrations into your floor. The large masses aren't perfectly uniform. Electrostatic charges accumulate where you didn't ask them to. You correct, cross-calibrate, swap materials, and still, 2 labs report G values that differ by 5, sometimes 10 parts in 10.5, bigger than their quoted error bars. Meanwhile, unknown to those fibers across the moon's face, a different experiment ticks every clear night. Apollo astronauts left retroreflectors on the lunar surface. On Earth, lasers ping them. Photons fly out, bounce, and return 2.5 seconds later. Stack that timing over decades and you build a ledger of the Earth, moon distance to millimeter precision. Lunar laser ranging isn't measuring G directly, it's watching gravity work. If G were drifting at any pace large enough to explain the lab spread, the moon's orbit would notice. It hasn't. The bound on .gg hovers near a few parts in 1013 per year. That's the solar system saying, if G moves, it does it softly, too softly to explain lab spreads outright. Parallel checks pile on. Planetary ephemerides, the tables that predict where Mars or Saturn will be, are tuned with radio tracking of spacecraft and radar echoes off planets. Those fits bake in general relativity and allow for a possible .g. The best solutions don't need it. Pulsar timing does something similar at higher stakes. Neutron stars in binaries act like gravity clocks, and their orbital decay matches gravitational wave predictions without extra drift in G. Even Big Bang nucleosynthesis, that early universe chemistry set, frowns at a different G back then. Change gravity's strength, and the primordial helium fraction shifts in ways the CMB and quasar spectra don't like. So what's with the lab puzzle? Impact lands here. Either systematic errors are nastier and more correlated than we thought, or G might be more slippery near matter at short ranges, or in environments where subtle forces masquerade as gravity. Teams chased both possibilities. Some built cryogenic balances to quiet thermal creep. Others used atom interferometers, dropping cold rubidium in a gravity field sculpted by nearby source masses. Atoms don't care about fibers, they care about phase. The results? Still a spread, smaller but present. New methods agree with some old values, disagree with others. The community keeps tightening bolts and sharing protocols, treating G as the least precisely known constant. This is where the field idea creeps back in. If a light scalar field couples feebly to mass, it could generate an additional fifth force, that looks like a slight tweak to gravity at certain length scales. Equivalence principle tests, like Ehret-Wash torsion balances comparing different materials, squeeze such couplings hard. Chameleon or symmetron models try to hide the field in dense environments and reveal it in vacuum, screening the force near Earth while letting it roam in space. But screening has to thread the needles we already set. Oklo's quiet reactor, clocks, null drifts, the moon's stubborn consistency. Human angle simple and small. A lab in a basement goes quiet after midnight. A torsion pendulum hangs in an evacuated chamber. The scientist logs the fibers twist every few minutes, sips cold coffee and writes no visitors on the door. Upstairs, someone drops a toolbox. The trace flickers. The next day, that data goes in the discard folder. You can feel the frustration, precision work haunted by footsteps. Across the hall, an atom interferometer team finally gets their vibration isolation to behave. The phase wraps less. Relief. Then the first full run returns a G that sits between the two warring camps, not a triumph, a sigh. Meanwhile, the moon reflects right on schedule. A photon launched from New Mexico returns and the station's ledger adds one more line to a stack that says G isn't wandering in any way the Earth, moon system can hear. The contrast is stark. Celestial mechanics gives serenity, the bench gives personality. What does it change? Practically, the metrology community admits G is the least precisely known fundamental constant and treats it with extra caution, building redundancy and blind analyses into campaigns. Theoretically, the split keeps scalar tensor gravity on the whiteboard. If a field controls couplings, it might dress masses differently in different environments, producing apparent G shifts where you least want them. Next to metal blocks near lab walls, inside vacuum chambers. It also keeps equivalence principle tests alive. If constants are sliding coordinates, then physics must ensure different materials fall the same, or reveal the failure in the 10th decimal place. Reveal, then pivot. Even with tight bounds from the sky and careful nulls from clocks, the G puzzle won't close. It's either a masterclass in experimental humility or a faint hint that constants are local settings, not stone tablets. If a field is setting the rules, then what we call constants are coordinates in that field's landscape. Tilt the field, the coordinates shift. That's not science fiction. That's scalar tensor gravity, dilatons, quintessence, theories where a dynamical field turns the knobs gently. If that's the suspect, it explains the pattern we've seen. Alpha whispers in starlight, Oklo fences possibilities, clocks listen hard and mostly hear quiet, and gravity refuses to sit perfectly still on a bench while behaving in the sky. The next step is obvious. Don't look for numbers to change. Look for the field that makes them look changed. Where would it hide, how would it talk, and which test forces it to speak? The scalar field suspect, when fields set the rules. If numbers won't sit still, maybe it's because something is nudging them. Not a new particle you catch in a detector, but a field smooth, everywhere, slow rolling like fog across a valley. In physics, fields set what's possible. Temperature fields tell you where ice melts. The Higgs field tells particles how heavy to be. So ask, what if there's a scalar field whose value tunes the couplings we call constants? Here's the stakes in plain terms. A dynamical scalar field that couples to electromagnetism can make alpha vary in time and across space. Couple it to mass, and you tickle gravity, changing how objects fall, how stars burn, how the universe accelerates. If the field has gradients, you might get a dipole in the sky. If it evolves with cosmic time, you'd expect slow drifts now, fenced by Oklo and our clocks. If it responds to local density, its effects could hide in cities and sing in space. That's a path that could reconcile quiet labs with loud hints. Action step by step. Start with scalar tensor gravity. General relativity says geometry tells matter how to move. Matter tells geometry how to curve. Put in a scalar that talks to curvature, and gravity's constant becomes a function of the field's value. Brand's Dick theory was the classic version. A scalar multiplies the Einstein-Hilbert term. Modern descendants add potentials and couplings to standard model sectors. Dilatons emerge in string-inspired ideas, fields that rescale lengths and charges. Quintessence is a scalar whose slow roll can drive cosmic acceleration instead of a rigid cosmological constant. These aren't decorations. They're mechanisms that let constants be coordinates in a bigger landscape. What nobody knew when quasar dipoles first made the rounds was how tightly a single field would link disparate tests. If the scalar couples to the electromagnetic sector, alpha feels it, and atomic clocks become antennas. If it couples to nucleon masses or the gluon field, nuclear resonance energies shift, and Oklo nails it down. If it couples universally to matter, the field mediates a fifth force, violating the equivalence principle unless screened. The same knob that moves alpha also tugs on torsion balances and lunar laser ranging. That's helpful. It's unforgiving. But there was one problem. Scalars you can feel are usually ruled out by how well we've tested free fall. Microscope-class tests push equivalence to parts in 1013 and beyond. Experiments show that aluminum and platinum fall the same to parts in 1013. A raw, unscreened scalar that modulates couplings would have blown that already. So theorists invented ways to hide the field when you're looking. Chameleon screening makes the field's effective mass grow with local density. In dense environments, the lab, Earth, the field is heavy, short-ranged, and quiet. In the thin intergalactic medium, it's light and free, able to drift and paint gradients across gigaparsecs. Symmetron and dilaton-like models pull similar tricks with symmetry restoration or environment-dependent couplings. Weather, not climate. Locally calm, globally breezy. Impact, if this picture holds, is a web of correlated signatures you can't fake. Sky dipoles, lab drifts, and fifth force whispers all tied together. Equivalence principle tests tight. Satellite experiments like microscope turn orbital free fall into numbers that slash the coupling space. Drop tower and atom interferometer campaigns chase micronewton anomalies over centimeters, looking for the faint flecks of a screened fifth force. Casimir force setups and torsion pendulums probe millimeter scales where chameleons might peek out. Meanwhile, the dipole amplitude and direction in alpha become predictions of the scalar's cosmic gradient. Clocks compare ticks at different heights, seasons, and compositions to catch time-dependent or potential-dependent modulation. Even the CMB gets a say. A rolling field during recombination shifts the Thomson scattering rate and acoustic peak positions, feeding straight into the Hubble tension debate. Human moment. A team wheels a vacuum chamber into a drop tower. Inside, a tiny test mass hangs from a gold wire finer than a hair. A camera watches for a twist when the tower goes weightless. The run lasts a few seconds, the data a few gigabytes, the signal, if it exists, buried in a tremor less than a billionth of a radian. Afterwards, in a quiet control room, someone traces a flat line with a finger and says, half joking, "We measured nothing again." Then they add the point to a plot that fences theories down to a corner. Meanwhile, theory sketches keep pacing. If a dilaton sets alpha, the coupling strengths to different sectors determine which experiments screen first. Tune the couplings and you can cook models where alpha varies at parts per million across the sky, while equivalence principle violations stay below today's caps. Add chameleon screening and you push lab fifth force searches into custom geometries and vacuum levels. But the leash is short. The field can't wave one flag in quasars and another in Oklo without a mechanism that knows context. The more data piles in, the narrower the path. There's a useful analogy that keeps people honest, weather versus climate. And I'm telling you, most days are calm, but the right instrument can still feel the breeze. The constants we write in handbooks are the climate averages we trust. A scalar field would make the day-to-day weather. Local density, gravitational potential, cosmic epoch, those are fronts and pressure systems. Most days are calm. Some days, if your instrument is quiet enough, you might feel a breeze. That frame doesn't excuse sloppy claims. It motivates targeted ones. Compare clocks of different composition in different potentials. Drag a clock up a mountain. Link Earth to a satellite with an optical time transfer. Map alpha with comb-calibrated spectrographs across the sky. Reveal, then pivot. If a field sets alpha, it can set other ratios too. The electron-to-proton mass ratio, the weak scale, even effective neutrino couplings. The more you allow to move, the more cross-checks you owe. That's where this story heads next. Stretch the field across possibility space, into selection effects, into why life lives inside a narrow window, and the question why these numbers turns into why here and now. Anthropic edges, life at the razor's tolerance. If a field is nudging the knobs, then the next question cuts close to home. How much slack do those knobs really have before the lights go out on chemistry, stars, and us? The answer most working physicists land on is uncomfortable, very little. The habitable space of parameters looks like a narrow ridge, not a plane, which means even a whisper of drift forces us to think like mountaineers. Where on the ridge are we walking, and how far before a misstep sends us into air? Start simple. Alpha sets how tightly electrons bind to nuclei. Tip it up and atoms shrink. Chemistry gets brittle, fusion thresholds in stars shift. Tip it down and electrons wander, molecules loosen, stellar cores change pressure balances. Then fold in the strong force. Nudge the strength that binds quarks in protons and neutrons and the deuteron, the first rung in nuclear building, can unbind halting stellar alchemy. Slide it the other way and diprotons might stabilize, letting stars burn too fast, too hot, racing through fuel before complexity can cool down and form. That's not theology. It's stellar structure with different inputs, and the outcomes swing hard. Now add the weak interaction. Change it and the balance of hydrogen and helium from the first minutes after the Big Bang moves, setting initial conditions for every star. So when people say fine-tuned, it isn't a slogan, it's a map with razor edges. In that map, carbon's story is a landmark. Inside red giant stars, 3 helium nuclei have to collide essentially at once to build carbon. The probability is vanishingly small, unless there's a specific excited energy level in carbon-12 that acts like a stepping stone. That level exists within a few hundred keV of the right place. Move nuclear couplings a shade and the resonance slips. Less carbon forms. Life, at least the biochemistry we know, loses its anchor. Here's where the drift idea complicates the picture. If constants vary across space or time, selection becomes local. We aren't asking why are the numbers globally friendly. We're asking why do observers find themselves where and when the numbers sit in the narrow window that permits them. Anthropic reasoning, stripped of hand-waving, is an observation filter. Of course you see a universe that allows you to be here to see it. But if the allowed window is razor-thin, then even a slow-moving field creates regions and epochs that are sterile. The ridge becomes a path through a patchwork of good and bad neighborhoods. Parallel to that thought runs a broader landscape story from theory. Inflation, our best sketch for why the universe expanded so smoothly early on, can produce multiple regions with different field values. In some models, quantum fluctuations during inflation push fields onto different ledges of a potential. String theory adds its own immensity, a landscape of vacua, each with its own low-energy constants, couplings, and particle spectra. If a scalar field decides alpha here and the weak scale there, the cosmic address book becomes a table of different settings. In that light, a dipole whisper in quasars is a local weather report on a vast climate survey. The human angle in this debate is quieter than a collider announcement. It shows up in late-night arguments over whiteboards. An astrophysicist draws a narrow band where stable nuclei exist. A philosopher circles selection effect and asks whether that explains anything or simply restates the obvious. A cosmologist shrugs and says, it's not an explanation of origin, it's a constraint on what we should expect to observe. Then someone pulls up a simulation. Wiggle alpha by 1 part in 10,000 and track how supernovae change their light curves, how stellar lifetimes shift, how planet-forming disks cool. The outputs don't coddle broad interpretations. They fence us in. What nobody knew when the fine-tuning conversations first heated up was how directly these questions would tie to today's tensions in cosmology. The Hubble tension isn't just a number fight, it's a physics fight. If electron mass or alpha tweak during recombination, the cosmic microwave background's peaks slide, changing our inference of the Hubble constant today. Drift becomes not only a story about life's window, but a potential lever on the Hubble tension. That's risky. One knob can't fix all mismatches without breaking something else, but it's a testable place to look. But there was one problem. Fine-tuning invites easy narratives, design, destiny, simulation, none of which earn a pass without predictions. The safer ground is empirical. Map which parameter shifts kill stars, which erase chemistry, which let structure form. Then ask whether a rolling field could thread through that maze without tripping Oklo, clocks, or free fall. If it can, we've reframed fine-tuning from a metaphysical riddle into a surveyable terrain feature. There's a micro-story that keeps the stakes human. A team updates stellar models with a slightly different alpha to mimic a hypothetical drift over billions of years. A postdoc watches the main sequence lifetime slide by a few %, enough to delay or hasten the heavy element enrichment of a galaxy. In the margin, they jot, biogenesis window shifts. It isn't proof of anything. It's a reminder that life's timing may be entangled with constants' timing. Impact lands like this. Varying constants turn why these numbers into why here and now. If the knobs flex, then our rulers for distance, time, and age are tied to relationships that might evolve. The multiverse becomes less an escape hatch and more a statistical claim about where observers can live on the ridge. And even without a multiverse, a single field with gentle gradients could make our patch a hospitable microclimate in a larger, harsher weather map. Meanwhile, experiments keep us honest. If selection is real, the field still has to obey our fences, Oklo's ash, the clock's quiet, the moon's millimeters. If it slips through, then the next implications are obvious and testable. Our cosmic yardsticks, standard candles and rulers, inherit that flex. And the age and size we quote for the universe become not only measurements, but measurements with context. That's where we go next. Cosmology on a moving floor, redefining age and size. While we were arguing about alpha and starlight and samarium and rock, cosmology quietly made a bet. That the physics of the early universe was the same physics we test on a bench. Every cosmic yardstick, standard candles, standard rulers, acoustic peaks, depends on that bet. If the knobs flex, the floor under our map slides. Start at recombination, 380,000 years after the Big Bang. That's when electrons and protons finally preferred to be married rather than free. The temperature fell, atoms formed, and photons decoupled, flying straight as the cosmic microwave background. The timing and sharpness of that transition depend on alpha, the electron mass, and G change alpha, and hydrogen's binding energy changes, shifting when the fog clears. Change the electron mass, and the Thomson scattering rate, the friction between light and matter, moves. Tug G, and the expansion rate at that epoch changes the pressure balance in the primordial plasma. All of that imprints the angular size and heights of the acoustic peaks in the CMB. Here's the stakes. Those peaks are our cleanest ruler. We turn their angular pattern into a physical scale, the sound horizon at recombination, and project it across the sky. Then we drag that scale down the timeline as a standard ruler and use it again in the later universe as baryon acoustic oscillations in galaxy surveys. Every step assumes the ruler's length is set by physics that didn't drift. Action step by step. Planck mapped the CMB with exquisite precision and under fixed constants, fit a universe with H around 67 km/s/MPC. Meanwhile, local distance ladders, Cepheids to Type Ia supernovae, landed near ~73. New gravitationally lensed quasars added an independent rung and often sided with local. The mismatch deepened, and the Hubble tension became a crisis, 5 to 6 km/s/MPC apart, beyond easy systematics. Into that gap, theorists tossed a careful question. What if the early universe constants weren't today's constants? If the electron mass were slightly higher at recombination, the ionization history changes in a way that lets CMB fits accommodate a higher H without wrecking the rest of the spectrum, up to a point testable with polarization and BBN. If alpha nudged, the same logic applies. An invited chapter spelled it out. Varying me or alpha shifts the CMB in specific, testable patterns and can ease the tension. Meanwhile, across town in a different pipeline, a cosmologist unlocked a single parameter. Allow alpha to float during recombination while anchoring it later with Oklo and clock bounds. The Markov chains ran. The posterior slid. The inferred H crept upward. Not a miracle cure. Pushed too far and polarization data complains. Big Bang nucleosynthesis pushes back, and damping tail features refuse to budge quietly. But the exercise changed the mood. Drift wasn't a metaphysical aside. It was a live nuisance parameter with leverage. Impact lands on our rulers and candles. The sound horizon depends on the speed of sound in the plasma and the timing of recombination, both alpha and me-sensitive. If its physical length changed, then bow measurements that assume a fixed ruler rescale, shifting inferred distances and, with them, curvature and dark energy parameters. Supernova luminosities depend on nickel yields and opacities tied to atomic physics. A drifting alpha would, in principle, bias the candle if you assume universality. Even gravitational wave standard sirens, clean in principle, rely on redshift measurements from host galaxies whose spectral features assume fixed transitions. The Webb is tight. There's a micro story that brings it home. A postdoc reruns a cosmology pipeline at 2 a.m. They toggle a flag. Me at recombination free. The plots regenerate. The H posterior broadens and shifts, living in a middle ground between Planck and the latter. They don't cheer. They draw a red box around check BBN, CMB damping tail, lensing. Hours later, a second run adds a prior from deuterium abundance. The box shrinks. The cursor hovers over save, then clicks. The note reads, sliding the floor moves the walls. Parallel action on another front. Daisy maps bow with dense redshift catalogs. Lensing time delays refine distances without candles. Gravitationally lensed quasars. Time delay cosmography lands near the latter's HA University of Tokyo. Affiliated team announces lens delays that bolster the high H side. Each method is proud of being independent, but all trace back to assumptions about early and late physics. If constants flex then stiffen, independence is conditional. What nobody knew when the tension first surfaced was how quickly instruments would adapt. Spectrographs with laser combs now aim not just for exoplanets but for a redshift drift measurement, the Sandage lobe test, to watch cosmic expansion change directly over decades. That test depends on spectral stability at the part per billion level, and yes, on constants staying put, or being modeled if they don't. If alpha drifts, the redshift drift signal gets a bias. Design teams now write constant variation systematics into their requirement sheets. But there was one problem. You can't fix everything by turning one knob, change one sector and three others push back. Raise me at recombination to help H, and you must not spoil the primordial helium. Nudge alpha and you must keep the damping tail and polarization happy. Change G and both BBN and the CMB acoustic scale stiff-arm you. The promise here is not a free lunch, it's a checklist. If drift explains the tension, it will do so with a consistent footprint across CMB temperature and polarization, bow, BBN light elements, and late time structure growth. Human moments thread through this too. A collaboration call turns quiet as someone says, our bow fit shifts if we adopt the varying me prior. Another voice adds, then we owe the CMB team a cross-check. No grand pronouncements, just the slow reweaving of a web where every strand touches the others. The reveal is simple and deep. Your cosmic address isn't a set of absolute numbers. It's a network of relationships that might evolve. Age, size, and expansion rate are conditioned on which constants you assume are fixed and when. If the rules flex, our map must flex with them. And if a field is the culprit, the moving floor ties the early universe to our labs and forces the next tests to speak to each other. Emergent constants, when reality averages out. We've been chasing knobs as if they're dials on a control panel, but there's another way to see it. The numbers we call constants might be the averages of deeper behavior, the way messy motion in a crowd turns into a smooth flow at a distance. In that frame, variation isn't the law breaking, it's the context changing. Start with something we already accept. Couplings run with energy. And get this, context matters as much as collision energy when the vacuum itself is part of the story. Push to higher energies in a collider and the strengths of forces slide because quantum fields are dressed by virtual particles. The renormalization group is the book that keeps score. Measured at one scale, the fine structure constant is one value. At another scale, slightly different. That isn't the universe cheating, it's the theory telling you context matters. Now extend that logic sideways. If environment, temperature, density, curvature acts like an effective scale, then low-energy constants could take on slightly different effective values in different space-time neighborhoods. Not new magic, just the same math, applied to where and when, not only to how hard you hit. Here's the stakes. If constants are emergent, we're not reading the source code. We're reading compiled output with optimizations that depend on the machine it's running on. The machine here is the vacuum, the ground state of fields, the pattern of symmetry breaking, the condensates that fill space. Change the vacuum a shade, by curvature, by background fields, by subtle finite temperature effects in the early universe, and the effective parameters you infer can drift without any Lagrangian parameter truly changing. It's reality averaging out. Action step by step. The Higgs field already set a precedent. Particles get mass because they move through a field with a non-zero value everywhere. That vacuum value isn't a number etched on a stone tablet. It's selected by the shape of a potential and the history that cooled the universe into one valley instead of another. In condensed matter, we live with this every day. The speed of sound in a crystal is constant until the lattice warms or strains. Then it shifts because the medium's microphysics changes. Light in glass seems to slow because the medium's degrees of freedom dress the photon. No one calls that a violation of Maxwell's equations. It's an emergent effective speed. Now pivot to the speed of light itself. C is invariant in the kinematics of relativity, but the speed limit that governs how fast information and interactions propagate can feel different in effective theories when the medium isn't empty. In some quantum materials, emergent relativistic quasiparticles race with a light speed set by the material's parameters. Those constants are real for the quasiparticles, emergent for us. Translate the analogy cautiously, and you see the move. The vacuum is a medium. If its properties vary across cosmic scales due to slow-rolling fields, topological sectors, or phase remnants from early times, our constants become the low-energy averages of that context. Impact arrives in how we interpret anomalies. A parts per million dipole in alpha from quasar spectra could be the footprint of a slightly different vacuum dressing along different lines of sight. Tiny differences in electromagnetic self-energy due to background scalar profiles. Oklo's razor-thin margins say the dressing barely budged here over 2 billion years. Clocks say the dressing is steady now within hard limits. Lunar laser ranging says gravity's dressing hasn't drifted measurably in the solar system. But emergent doesn't mean loose, it means correlated. If one sector's effective parameter slides, others can compensate because the vacuum state ties them together. You get drift that's structured, not arbitrary. Meanwhile, something else was happening in theory offices. The renormalization group story grew teeth in curved spacetime. Curvature acts like an infrared regulator. Background fields shift beta functions. Thresholds for particle species turning on or off depend on temperature and density. A cosmologist sketches a flowchart on a pad. Early hot plasma right arrow, different screening right arrow, shifted recombination microphysics. late cold vacuum right arrow today's values. The arrows don't invent new forces. They remind you that constant lives at the end of a long cascade of averaging. Human moment because even abstractions need fingerprints. A theorist stares at a beta function and mutters, "It's a story." Hold on, what they mean is the vacuum edits the cast and the plot twists look like running. They mean it. The slope of that function, the way a coupling runs, isn't a dry derivative. It's a narrative about which degrees of freedom are active, which symmetries are broken, which backgrounds you've assumed. Shift the context, and the story ends on a slightly different page. In a notebook margin, they write, "Constants equals summaries." But there was one problem. Emergence can excuse anything if you let it. You can drown a real signal in effective hand-waving. That's where the fences we've built matter. Emergent or not, the effective constants must hit Oklo's ash, clocks, nulls, and the CMB's peaks. The renormalization group gives you quantitative handles. You can compute how much a background curvature or a scalar profile would shift an effective coupling, and test it against every dataset in the Webb. Reveal, then pull the thread. If constants are emergent, context dependence stops at energy. It spreads to space-time environments. That bridges the scalar field suspect and the cosmology floor. The field sets the background. The background sets the effective numbers. The instruments measure the averages. Stretch that logic one more notch and an awkward thought enters the room. If our laws are the averages of deeper rules running on a substrate, then what we call constants might be settings chosen by statistics. And if statistics is the renderer, someone will eventually ask whether the renderer is computational. We're not going there yet, but the door is now open. The simulation trap. Are constants just config files? Stretch the emergent idea one notch further and a blunt question lands. If our constants look like outputs of a system that averages, updates, and context switches, are we reading configuration files rather than laws? I'm telling you, this is where people lean in. Not a neon "we live in a simulation" sign, just the uncomfortable symmetry. Settings versioned, environments compiled. And yes, humans notice patterns like that because we build worlds that way. Here are the stakes. If constants vary, maybe they're not carved into nature. Maybe they're parameters in an algorithmic substrate whose constraints show up as finite precision, anisotropies, and occasional seams. That doesn't mean joystick-wielding operators. It means computation as physics, a universe that evolves by rules that look like code when you squint. If that's true, edits are possible in principle, and the right kind of drift would look like a patch rolling out. Action in 3 beats. First, the algorithmic line. Cellular automata, lattice models, and discrete spacetime proposals show how continuous-looking laws can emerge from update rules. If space is granular, Lorentz symmetry becomes an approximation that holds until you hit the lattice scale. Push high-energy particles across that grid, and you might see tiny direction-dependent effects. Constants that we treat as continuous could inherit tiny rounding quirks. If those quirks drift as the machine optimizes, you demeasure a slow walk in alpha without anything mystical moving. Second, discrete time and computational cost. Landor taught us that erasing 1 bit has an energy price. Margolis, Levitin showed that computation rate is bounded by energy. If the universe computes, there's a budget. That budget sets ceilings on clock stability, measurement precision, and how fast information can spread. A renderer under constraint might smear transitions by a few parts in 1018 simply because no physical system can update every voxel infinitely finely. Atomic clocks would approach that horizon and start to hear the ceiling as flicker you can't engineer away. Not a bug, an architectural limit. Third, patch dynamics. If the substrate favors local consistency, not instantaneous global agreement, then the parameters that define low-energy physics could converge asynchronously. A ripple in settings would propagate at a finite speed, leaving behind small anisotropies. A spatial dipole in alpha. In this frame, it's a synchronization front. Gravitational potential wells could delay the front slightly, modulating the drift by environment. You wouldn't see jumps. you'd see slow, correlated nudges with a geometry. Caution is the next beat. Philosophy can sprint here faster than evidence. So what would count as seams? Finite precision artifacts would look like plateaus in measured ratios where you expect smooth variation, quantization where none belongs. Anisotropy aligned not with known structures but with a computational grid, say, a preferred axis that shows up across unrelated datasets, would be suspicious. Patch updates would look like time-localized, bandwidth-limited changes, a transient in multiple constants that roll out with a speed limit. None of that has shown up cleanly. The Hubble tension is a mismatch, not a glitch. The alpha dipole is a tease, not a checksum. Meanwhile, information theory keeps pulling this thread back to testable ground. Black hole thermodynamics turns area into entropy. The holographic principle says the world's degrees of freedom scale with surface, not volume. Those are computational statements in disguise. Storage limits, bandwidth caps, compression theorems written on space-time. Here's the thing. Information is the only ledger that never looks away. If anything is constant through drift, it might be those information bounds. Constants can slide. The ledger of bits stays balanced. Human moment stripped down. A researcher sits in a dim office and stares at a list of residuals that won't die. They pull a sticky note off the monitor where someone wrote "check the comb." They rerun a calibration. The residuals soften. It wasn't code. It was the lab's own software misreading a thermal correction. Relief, then a whisper they don't say out loud. If we can mistake our own system for a seam in reality, how careful do we have to be before we claim the universe is debuggable? There's also the dread. If constants are config files, then edits exist in principle and so does rollback. That's a psychological hook. Agency meets cosmic settings. The thought isn't about cosmic administrators, it's about agency at all. It cheapens causality in a way that makes people flinch. That's why the responsible move is to pin simulation to predictions, not vibes. Discrete spacetime should leave dispersion in gamma-ray bursts at high energies that scales with distance. Preferred frame computation should bias ultra-high-energy cosmic ray arrival directions. Finite precision should cap entanglement depth in ways that diverge from quantum field theory. Those tests are hard, but they're specific. Reveal, then pivot. Even if no simulation seam ever shows, the information view doesn't go away. Landor's cost and the holographic bound set the scale for how stable clocks can be, how dense memory can get, how fast we can interrogate constants. They're the rails. If alpha drifts, the measurement of that drift is throttled by those rails. Which brings the story home. Even if constants are config files, the only way we'd know is by pushing up against the limits set by information itself. So we keep both pictures in hand. Constants may be emergent summaries shaped by a field. They may be rendered settings on a deeper substrate. Either way, the seams, if they exist, have to show up in the same places, in the timing of black holes, in the bandwidth of clocks, in the gentle biases of spectra stretched across the sky. And when you ask what never budges through all of that, one answer keeps stepping forward: the rules of information. Information is the real constant, from black holes to qubits. If anything refuses to bend with the drift, it's not a number, it's a limit. Information sets those limits. You can change couplings by a whisper and nudge spectra by parts per million, but try to cheat the bookkeeping of bits and the universe snaps back. Black holes were the first hard lesson. Here's the stakes. A black hole isn't just a mass with a shadow. It's a warning label about information you can't ignore. It's an entropy machine. Bekenstein argued that there's a maximum information you can pack into a region before it collapses, and that cap scales with the area of the boundary, not the volume. Hawking added heat. Black holes radiate with a temperature that lets them evaporate. Put those together and you get a bound. How many bits can fit on a surface of given area? The holographic principle pushed it further. The deepest description of a region is encoded on its boundary. That's an accounting rule. Constants can slide. The ledger must balance. Action step by step. A student stares at the Bekenstein bound. The entropy S is less than or equal to 2 pi h/c. Translate it and it says energy and size cap information. Landor tells you the cost per bit flip. Erase 1 bit, spend kT ln 2 of energy. No exceptions. Not even for you, not even for the universe. Margulis, Levitin gives a speed limit. A system with average energy E can't execute more than 2 e/pi logical operations per second. These aren't taste preferences, they're guardrails. Build a clock and you face all three. Its stability is throttled by how well you can store and manipulate phase information without paying too much entropy, too much energy, or too many operations. Meanwhile, gravity turns these abstractions into scenery. Throw a notebook into a black hole and information seems lost. But the holographic ledger says no. It's smeared on the horizon's degrees of freedom, then trickled out in Hawking radiation. What nobody knew at the time became the central fight of a generation. The information paradox, the firewall debate, the page curve. Recent calculations in quantum gravity show the radiation's entropy rises then falls. The curve you'd expect if information comes back out. However, the constants flex inside the action. The information book closes clean. Impact lands in the lab. Quantum metrology, using entanglement and squeezing to sharpen measurements, now reads like a manual for flirting with these limits without overpaying. Want to hear alpha drift at 1018 per year? You can't just count more ticks. You need better bits. Entangle atoms so their phase uncertainty shrinks below the standard quantum limit. Squeeze light so one quadrature carries less noise. Every decibel of squeezing and every extra qubit of entanglement pays rent in energy and entropy. Landor sits at the door with a coin box. Here's a micro story. A clock team locks a laser to a cavity and then to a strontium transition. The pi texts the grad at 3 a.m. Beat note stable. The reply is a photo, 2 razor-thin lines, perfect. You can feel the relief through the screen. They add squeezed light, buying a few decibels against shot noise. The instability plot drops. A postdoc taps a whiteboard where someone scrawled Heisenberg scaling and says, "Not for free." The room laughs, tired. They know the rule: push noise down in one place, and it pops up as heat, decoherence, or engineering pain somewhere else. The bound isn't a suggestion, it's a ceiling. Parallel action. Communications engineers try to beam time across continents. They fight fiber thermal noise with phase stabilization, then hit nonlinearities that twist the signal. They route via satellites and meet ionospheric scintillation. Every fix swaps one noise for another under the same ledger. In a control room, someone mutters, "We're arguing with nature's accountant." Nobody disagrees. Now pull the thread back to black holes. The holographic limit scales as area over Planck length squared. That number hides constants h/c/g inside it. If those constants drift, the Planck area would slide. But the operational statement survives. Whatever the microscopic details, there is a maximal information density and a maximal processing rate consistent with causality. If a scalar field flexes alpha or μ, those bounds might be dressed, not broken. The budget reallocates, the total stays put. And there was one problem. If information rules, why do our best detectors still talk about calibration drifts instead of entropy budgets? Because we're only now close enough for the bounds to glare. A network of optical clocks at 10, stability starts to touch Landor's floor per recycled bit and Margulis, Levitin's pace per stabilized mode. Gravitational wave interferometers squeeze light to hear spacetime itself. LIGO's quantum noise isn't an engineer's failing. It's the bound saying hello. Reveal, then connect to drift. If the cosmos lets couplings wander while conserving information, measurement becomes a duel of slow motion. The field moves the target by a hair. You use entanglement to narrow your aim. Landor taxes your error correction. Margulis, Levitin caps your update rate. The holographic ledger says you can't pile unlimited certainty into a finite lab. So your only winning move is to coordinate. Link clocks across continents, pool entanglement, and integrate for years. That's not a metaphor. It's the playbook many labs are already running. Human moment to end it clean. Two teams on opposite sides of the world compare ticks through a stabilized fiber. The residuals look like static until they fold a year of data and see only flatness. No signal yet. They don't sigh. They bookmark the plot and say, next year. Get this, the patience is the point. Integration time is a weapon. The message under the silence isn't defeat. It's the universe saying, the rules of information are the rails. If the constants drift, ride those rails long enough and you'll hear it. The personal fallout, your clock, your life, your causality. This stops being cosmic the second you check your phone. Every timestamp you trust, bank transfers, medical records, stock trades, airplane schedules, rides a chain of synchronized clocks. Those clocks assume the constants underneath don't slide. If they do, even by a breath, the entire trust network has to learn a new habit, recalibrate often and together. Start with GPS, the quiet heartbeat in your pocket. Satellites carry atomic clocks, correct for relativity and broadcast time. Your phone triliterates its position by comparing arrival times of those ticks. Now insert a whisper. If alpha drifts, the microwave transitions in those spaceborne clocks shift ever so slightly. If a scalar field couples to gravitational potential, the drift modulates with altitude and orbit. If the electron-to-proton mass ratio flexes, the oscillator physics shifts by different amounts in different clock species. 1 part in 1015 isn't a headline. It is a street where ambulances miss a turn if the whole network doesn't pull in the same direction. Semiconductors feel it too. The band gaps that set transistor behavior depend on fundamental constants. No, your laptop won't melt if alpha changes by a billionth, but semiconductor fabs already live at the edge of tolerances. A global standard update that nudges reference voltages or frequency standards ripples through testing suites and firmware updates. Quietly, engineers write patches because metrology tables moved a decimal whisper. Hospitals live by isotopes. PET scans rely on positron emitters. Cancer treatments calibrate dosages to decay rates and detector efficiencies linked to atomic physics. Revisions to fundamental constants won't rewrite nuclear half-lives overnight, but they will force equipment calibration labs to reissue certificates, rerun quality assurance, and for a few weeks, block out machine time that would have scanned patients. Nobody tweets that. It just happens at cost. There's a micro-story in that shuffle. A national standards lab publishes an update, a revised recommended value for a combination of constants used to derive a secondary frequency standard. Slack pings light up. Do we patch tonight or wait for the weekend window? The email lands in a telecom facility at 4 a.m. A technician in a quiet room opens a sealed drawer, pulls out a rubidium reference, and uploads a new calibration file. Outside, cell towers keep humming. 2 days later, a satellite's timekeeping software applies a small correction. No news alert, just a global heartbeat that skipped and resettled. Meanwhile, financial exchanges measure time in nanoseconds. Co-located servers execute trades with determinism that courts now scrutinize. Any drift or redefinition has legal consequences, which clock defines before and after when money moves faster than news. Regulators already require traceability to national time scales. If those scales shift because we redefine the second in the optical, entire rulebooks need revisions. You'll never see the committee meetings, but the argument over causality will be spelled out in billable hours. Here's the uneasy part. We think causality is obvious, a happens, then B, but causality at scale is a network phenomenon. It's enforced by synchronized timestamps across distributed systems. If constants drift, even within fences we've drawn, raw oscillator physics shifts unevenly across clock types. Until a new definition corrals them, two equally correct clocks might disagree in a pattern that isn't just relativity. That's not philosophy. It's whether your car's collision report and the other driver's dashcam agree on the minute when two signals crossed. Industry already knows the mask we wear. We call laws constants and build conventions around them. When the SI redefined the kilogram by fixing Planck's constant, nothing heavy got lighter, but calibration chains rippled. If the second moves to the optical and constant tables tighten to new values pinned by lattice clocks, your phone won't blink. The power grid might. Phasor measurement units that stabilize transmission lines depend on phase-synchronized time. A microsecond error grows into a misaligned grid if you multiply it across a continent. So operators rehearse the switch years in advance. There's a human moment at every layer. A software engineer in a basement data center stares at a log, an authentication token rejected because its timestamp disagreed with the authorization server by 200 nanoseconds. They trace the bug to a firmware update that changed a clock's disciplining loop. The fix is a single line. The lesson sits heavier. We treat time as a given. We survive by version control. Meanwhile, something else was happening in places people rarely consider. Surveyors roll portable optical clocks into vans and park them on mountaintops, calibrating national height systems with time dilation. A water authority checks aquifer levels by reading slight gravitational potential changes in clock frequencies. In a lab, a graduate student tunes a microwave synthesizer by a few hertz because the new constants table says the old value was off in the last digit. They stick a note to a cabinet, constants updated, instruments not. What nobody knew when this debate began was how personal it would feel once the second itself sits on the table, because your life runs on timestamps you never see. Redefine it, and every timing protocol, NTP, PTP, satellite time transfer, needs a new handshake. Not dramatic, just relentless. Firmware, procedures, training, audits. The world keeps moving because people treat timekeeping like plumbing. Boring, essential, thankless. If constants aren't fixed, certainty isn't either. We'll adapt, we always do. We'll pin our units to atoms that can also warn us when the pins slip, but the feeling changes. You don't stand on stone. You stand on standards, revised in footnotes, carried by people who wake at 3 a.m. to keep your life in order. Your causality is built, maintained, and if the universe breathes, updated on schedule. The coming experiments, how we'll break or confirm reality. Next comes the gauntlet. Laser comb spectrographs map alpha across redshift and sky. Spaceborne optical clocks compare ticks from orbit to mountaintops, hunting potential coupled drift. Lensed quasar time delays, bow from Daisy, and CMB recombination models crosslock parameters. Global clock networks listen for scalar breezes. Torsion balances and atom interferometers press equivalents to new decimals. A single, consistent anomaly, same phase, same direction, same amplitude, tips the balance from nuisance to signal. And if that happens, you'll remember where you were when reality blinked. The meaning and the dare. If constants are settings, causality is maintained, not guaranteed. Subscribe, stay skeptical, and watch the next investigation, where clocks, quasars, and the moon's mirror decide whether reality flexes or we misread our instruments.